indicates this is going to be about some relation between representation theory of something with fine algebra and some new geometric objects which we call schemes of band. So let me give you first a little bit of motivation and context. So the original motivation came from a recent joint paper with David Hernandez and Christophe Geis, where we studied relations between shifted quantum affine algebras and cluster algebras. So the main result of this paper is very much in the same flavor as this morning lecture of David. The idea is that we have a certain category of representation which has a Grothendieck ring, and then we show that there is a cluster algebra structure on this Grothendieck ring. And this is interesting, for example, to understand when tensor products of simple modules are again simple, or questions of this type. So the only new feature, the main new feature in this paper compared to what we saw this morning is this blue shifted thing. So shifted quantum affine algebras are some new classes of algebras which were introduced by Sasha Tsimbayuk and Misha Finkelberg in the end of the around 1918, I think, 17. And their representation theory was studied by David, and then we tried to find some relation with cluster algebra in this paper. And one of the results of this paper is that the Grothendieck ring of this category of representation coming from shifted quantum affine algebra contains lots of copies, lots of subalgebras isomorphic to the coordinate ring of the simple algebraic group G of the same type, of the same ADE type. So this motivated me for trying to find something that generalizes the coordinate ring of G, but which could be an infinite dimensional, the coordinate ring of an infinite dimensional variety, which could be isomorphic to this Grothendieck ring coming from shifted quantum affine algebras. And the inspiration for this geometric object came from some group of papers by these authors. So first by Koroteyev and Zeitlin, and then together with Sage. And then there is another paper with Eduard Frenkel, and then another paper by Koroteyev and Zeitlin. And it's all about what they call Q-oppers. So Q-oppers is some geometric version of Q-difference operators. I'm not going to give any definition about this, but you can refer to this paper. And one important result in their papers is that they show that in this setting of Q-oppers, there are some interesting functional relations which appear, which they call QQ systems. And it turns out that QQ systems were also a fundamental idea in our paper with Christophe and David. So I was puzzled by the appearance of QQ systems in these papers, which we use so much in the cluster structure of the previous paper. And so then I started a project with Luca, who is here, and we wrote the first paper where we introduced these DC bands and proved that the same cluster algebra structure occur in this setting. And our definition of this DC band was very much influenced and inspired by this geometry of Q-oppers. But then later we continued to investigate this geometry, and then we realized that in papers much before that, in the 1980s, there were some interesting papers even more relevant to the definition of these bands by Frenkel, Rezhetikin, Selenov, Tianshansky, and Sebastianov. And this was about Q-difference Drinfeld Sokolov reduction and the relation with the Q characters. And so we wrote a second paper where we tried to explain how our GC bands were arising very naturally from the ideas of this Q-difference Drinfeld-Sokolov reduction. And this allowed us to prove, in fact, with the node conjecture of Frenkel and Reshetkin on the geometric description of the Q-character homomorphism. So the Q-character were introduced by Frenkel and Reshetkin in these years, 1998, and they have been very much studied since then. David mentioned them this morning. These are the notion of characters that are suited for finite-dimensional representation of algebras. And in their paper, Frenkel and Reshetkin mentioned that conjecturally there should be some description, some geometric description of this Q-character homomorphism using this object, which I will explain later, this Q-different Drinfeld-Sokolov reduction. And so we managed to check this. So here is the plan of the paper, of the lecture. First, I will give you the definition of GC bands. You will see it's quite elementary, in fact. And then I will explain the cluster structures on their coordinate rings. And then I will explain this Frenkel-Reshetkin conjecture. So, as I said, this is joint work with Luca Ancone, and we have two preprints on the archive, which you can check if you are interested. Right, so I need some notations coming from theory of algebraic groups. So, during this talk, G will always be a simple algebraic group of type ADE over the complex number, and I will assume that it is simply connected. Okay, then R will be the rank of G, and C will be the Cartan matrix associated with G, or with its Lie algebra. Now, since this group is supposed to be simply connected, all the characters of the Lie algebra can be lifted to the group. So in particular, the fundamental characters, the characters of the representation of the Lie algebra with highest weight, the fundamental weights, they can be also regarded as characters for the group. And I will denote them by chi1, chi-r. So these are the fundamental G modules. Okay. Then we will have to use a fixed Borel subgroup B with maximal torus T, and also the opposite one, B minus, with respect to this torus T. Then we will denote by U and U minus their unipotent radicals. We will need the Weil group. So the Weil group is by definition the quotient of the normalizer of the torus by the torus. And in the Weil group, we are going to fix a Coxeter element C. So Coxeter element means just the product of all the simple reflection, once each, in a given order. And by C bar, I will denote a representative of C inside the normalizer of T. So C bar is some element in G, in fact. Okay. Now, with this datum, we can define a unipotent subgroup. In fact, with every element in the Weil group W, you can define a unipotent subgroup U of W, which is of dimension the length of W. And it is defined like this. You take U and you intersect with the conjugate of U minus by this element W. So if you do this with a Coxeter element, you get a unipotent subgroup of dimension the rank of G. So I will denote it by U, C inverse. So sorry for all this notation, but I will need that. Now I can define, well, first let us go even back, further back in history, and let me state a very beautiful result of Steinberg, which is called Steinberg's cross-section theorem, and which goes back to the 60s. So we define A of C. So A of C I will usually abbreviate just by A, but you should remember that this A depends on the choice of Coxeter element. And so this is just this intersection. You translate U by C bar on the right, U minus by C bar on the left, and you intersect. Or you could say it's equivalent. You take this unipotent subgroup of rank R, of dimension R, which I had before, and you translate it from the right by C bar. So it's going to be some subspace inside G, which is an affine space of dimension R. Right? So geometrically, it's just an affine space. But it is realized in a certain way inside the group G itself. And what Steinberg proved is that if we consider this map, we take an element in the group G, and we map it to the R tuple of evaluation of the fundamental characters to this element A. So remember, chi1, chi-r are the fundamental characters. For example, if we are in type A, if we are with SLN, these fundamental characters are just the characters of the external powers of the fundamental of the vector representations. So we have R of them. You calculate the character on A, and then you obtain a certain element in C to the R, and this gives an isomorphism. So the fact that we have an isomorphism is not something new, because, as I said before, UC minus 1 is an affine space, is isomorphic to an affine space of dimension R. If you translate it by C bar, you still have something which is an affine space of dimension R. But the point is that this precise map gives you the isomorphism. And from this, Steinberg deduces that A is in fact a cross-section of the set of regular conjugacy classes. So what is a regular conjugacy class? A regular conjugacy class is the conjugacy class of an element which is of maximal dimension. The maximal dimension of a conjugacy class in G is the dimension of G minus R. So, of course, you have also elements which have a much smaller conjugacy class, like the identity element. But this is a maximal dimension. And if an element has a conjugacy class of this dimension, we call it regular. This is in the sense of Steinberg. I don't assume that it is semi-simple, for example. Okay, and so the statement of the theorem is that all the elements in A are regular in this sense, and every regular orbit is intersecting A in a single point, right? So now this implies that we can think of the coordinate ring of A. We can think of the coordinate ring of A as isomorphic to the character ring because of this thing here. The character ring of G, we are in simply connected situation, so the character ring of G is just the polynomial ring in the fundamental characters. And now, because of this, we can identify this polynomial ring with the coordinate ring of A. So we have somehow find inside of G some affine spaces which realize the spectrum of the character ring. And we have one of them for every choice of Coxeter element. Okay, so this will come back later in the talk when we discuss Kirillov-Reshetikhin conjecture, but for now I just want to to emphasize that this space A is not something arbitrary, and that it was already used in the literature for good reasons somehow. And it's going to be used in our definition of the GC bands. So now I can pass to the, well, maybe some question before? No? Then let's define GC bands. The definition is completely elementary. So we fix a Coxeter element C, we have G, and then we consider sequences, infinite sequences in both directions of elements of G, so G of S. And the requirement is that GS plus 1 inverse belongs to this Steinberg cross-section for every S. So you can think of this as a sort of dynamical system inside G, discrete dynamical system, where the transition from GS to GS plus 1 is by multiplication by an element of this cross-section A. Right, so why not? Let me state immediately the proposition. So these GC bands, if we put all of them together, we can regard them as rational points over C of an infinite dimensional affine scheme, which I will denote by BGC. And if we look at the coordinate ring of BGC, which will be denoted by RGC, this is a unique factorization domain. So we have something infinite dimensional, but still somehow well behaved. And it's not so difficult to prove this proposition. I can give you a sketch of proof. The idea is very simple. Suppose you have a band B, so this is a sequence G of S, and so you can calculate for every S this GS plus 1 inverse. So by definition, this is in A, the cross section, and we can form the sequence of all these elements in A. And now the claim is that the map, which takes a band B and maps it to its zero component times the sequence A here, this map is a bijection. And this is almost obvious, because if you fix yourself an arbitrary element in G, G0, and an arbitrary sequence A in A to the Z, then you can calculate G1, G2, or G minus 1, G minus 2 just by multiplication of G0 on the right or on the left by the components or the inverses of the components of A. So it's obvious to construct an inverse to this map. So we have a bijection, and now it's well known that G is an affine variety, and A to the Z is an infinite dimensional affine space, because it's just an infinite product of copies of an affine space A. So the whole thing is an affine scheme. It's infinite dimensional, but it's not a problem. And what else? Yes, then G is also known that its coordinate ring is a unique factorization domain. And of course, then when you multiply by an affine space, you keep this property, so you get also the second point. Yes?
So in case of GLN, what is this A? Is this just diagonal?
Okay, this comes actually right now. Thank you for the question. But this is now the example of SLN. So if you take SLN or SLR plus 1, and if you take the standard Coxeter element, so S1 times S2 times SR, then it's a little exercise to calculate this Steinberg cross-section. You will get exactly all the matrices of this form. So I'm sure that everybody recognizes these matrices from algebra 3 or algebra 2. So in France we call them matrice compagnon. I don't know if this is also the same in other countries, but yes. So these are all the matrices where you have ones under the diagonal, and then here arbitrary numbers, and then a minus 1 to the r, so that the determinant is equal to 1. We want to be in SLR. Okay, and you see that it is indeed an affine space of dimension R, right? Now, what does it mean to satisfy the band condition? So if you have two matrices G and H such that GH minus 1 belongs to this, then it means that you obtain G by multiplying H by an element of A, and this multiplication, because of these lines here, it means that the rows, the R last rows of G are equal to the R first rows of H. So these are R+1 square matrices, but then they differ. You pass from one to the other by shifting one side down and then adding a new row. And so this means that you can encode. So then a GC band in this case will be a sequence of matrices like this, where you just keep the last R rows and they become the R first rows, and then you continue. So you could just superimpose these matrices where they coincide, and then instead of having an infinite sequence, you have just one single matrix, which is infinite like this, and we call this a band, for obvious reason. So therefore, an SL R+1 CST band B can be represented by an infinite matrix like this. And so the only condition is that every submatrix consisting of R+1 consecutive rows has to be in SLR. So it has to have determinant 1. Otherwise, it's an arbitrary matrix, right? Okay. But I warn you that even for SLN, if you take a non-standard Coxeter element, then the description will be different somehow. It really depends on the choice of Coxeter element. Okay. So now, from this definition, we can immediately see that we have a G action on this scheme, just by right multiplication on every component of the band. So you see, if you have a band B, which is G of S, and then you fix an element H in G, then if you consider the sequence GS times this fixed H, then because of this obvious equality, you will stay inside the space of bands. So this means that we have a right action of G on the space of bands, and this induces a left linear action of G on the coordinate ring of G of this space of bands. And again, because of this relation, you see that if we look like before at this space of bands, this product G times A to the Z, then when we act on an element here with H, it means that here we act on this G factor by right multiplication, but we don't do anything on the A of Z. So it's just a kind of obvious action. It's only on the left factor. And as a consequence, if we are interested in the G invariance for this action in the coordinate ring, then this G invariance, well, the action of G on G by left translation has no invariant. So it means that the invariance will be just the second factor. So we can identify this G invariant subalgebra to the coordinate ring of A to the Z. And this will be quite important because, well, in the sequel, when we will connect this with quantum affine algebra, this C of AZ will become the Grothendieck ring of the category of finite dimensional representation. We already said several times that these are polynomial rings, so coordinate rings of affine space in infinite dimension. But now we will have a sort of new way of seeing it as a G invariant of something more complicated. And this is going to be extremely useful. Okay. So what is the A now? We have this coordinate ring, RGC, and it contains interesting subalgebra. So for example, this RGCG, the G invariant, but we can also consider the U invariant, where U is the unipotent radical of B. And we are going to concentrate on this plane of algebra and to look for a cluster algebra structure on each of them. In fact, on a cluster algebra structure on the big one, which restricts to cluster subalgebras on the smaller ones. Yes, so, okay, as we saw this morning, in order to introduce cluster algebra, in order to define cluster algebra, we need to to find initial seed. So this is this initial combinatorial datum from which you produce by mutation many other elements in your algebra of interest. So this means that we need to have some starting point, that is some subset of interesting coordinate functions on this scheme in order to get started. So let's start by looking at some natural coordinate functions on this scheme of bands. So, yes, so by definition, the scheme of bands is contained in the infinite product of copies of G indexed by the integers. So we can project on one component, right? So if we fix an integer s, then we have a natural projection from BGC to G, where we send the band GT to just the component number s. And now this means that when we go to the pullback, we get an embedding of the coordinate ring of G inside the coordinate ring of RGC. And we get this for every s. So this, I told you before that this is the kind of thing that we noted in our paper with David and Christophe. This was the kind of property that we noted for the Grothendieck rings of shifted quantum affine algebra. Anyway, so we have these embeddings, and now we can use natural coordinate functions of G on G, and then pull them to the. And what are the natural coordinate functions on G? Here I'm going to use something which has not been discussed before, I think, in this week, but I hope some of you at least know this. These are the so-called generalized minors of Fomin and Zelevinsky. So if you are not familiar with them, just think in terms of type A. So in type A, G is SLN, and generalized minors are just minors. So every minor, that is, you fix a number of rows and columns, and you take the determinant on these rows and columns. This gives you a certain regular function on SLN. And you can do this for any choice of rows and columns. So you get a bunch of regular functions. The smallest one are the entries of the matrix. The biggest one is the determinant itself, but this is constant equal to 1 because it is SLN. So you have a bunch of minors. And in general, you can do the same. And we denote these functions by delta, and it is indexed by two weights, so which are obtained by acting with the Weil group. V and W are elements in the Weil group. So you act with V and W on some fundamental weights pi I, and in the type A case, these two indices correspond to the subsets of rows and columns of your minors, right? So for each datum of a fundamental weight and a pair of elements of the Weil group, we have a certain regular function which is called the Fomin-Zelevinsky generalized minor, and then we can lift it to this RGC, and then we get something which depends also on S, so I add this upper index S, and we get in this way some functions. Okay.
So in general, these are, you take matrix elements and the fundamental representations, but only the ones that are in this Weil group orbit?
Well, at this stage I take all of them, but sometimes later we will specify maybe some of them. But here at this stage we could take any of them. And so it means, in other words, that this function applied to this band is just this minor applied to the S component of this band, right? It's just okay. So the proposition is that these functions generate the coordinate ring. We have enough functions to generate a coordinate ring. It's not totally obvious, but the proof goes as follows. We first prove that images of this coordinate ring of G by all the embeddings pi S star generate the coordinate ring here, if we put all of them together. And then we just have to go back to this coordinate ring of G, and this is a result the recent result of Hironori Oya, that the generalized minors of a group of type ADE generate the coordinate ring. Okay, so if we put all this together, we get a bunch of functions which at least generate. But they are not independent, almost obviously. For example, if you think in type A, we would have all the minors of this infinite matrix here. But they are depending on this S. And what means S? S means which level in the infinite matrix you are talking about. And so it's clear that some minors of the matrix G of S are identical to some minors of the matrix G of S plus 1, by definition. So there will be some relations, and more generally we will have so-called gluing formula, which take the following shape, that we will have equalities between some minors like this, where we go from upper index S to the upper index S plus 1, but at the cost of shifting the row indices, and the row indices in this general setting are shifted by replacing the Coxeter element Ck by Ck minus 1. And so in order, this is going to be for all k between 1 and mi, and mi is defined like this. So don't worry too much about the details of the formula, but it's a sort of important formula. Okay, then in fact the proof is not very complicated, and well, let's say it can be checked using properties of generalized minors, and for example I refer you to the paper of Fomin and Zelevinsky where they introduced them. They showed many interesting identities. So anyway, we have this. Now I will also need coordinate functions on the affine part, so the A to the Z. And for this, I'm going to call them in a different way. They will be defined in terms of generalized minors, but I will denote them by theta IKS. So what is the idea? We take a band G of t, and then we apply the so-called principal minors, so without any element of the while group, just pi I. But we apply this to the product of GS and GS plus K inverse. So GS times GS plus K inverse is equal to GS plus 1 inverse multiplied by GS plus 1, GS plus 2 inverse, etc. So you can see that this is going to be, by construction, something which will be in A. And so, what do I want to say? This is going to be something which will be G invariant, by what I was saying before about the action of G. So here you get not only regular function on RGC, but regular functions which are invariant by G, because the G action would correspond to multiplying from the right by some H here, and from the left on this factor by H inverse, so you don't change anything. So you get, in fact, inside this, we get inside the coordinate ring of A of Z, and this is an affine space, and in fact we can show that it has polynomial generators given by all the elements of the form theta I1 in this parametrization. So if you take all the k's, you have too many, but if you just restrict to the theta I1, you have a polynomial generator for this polynomial ring. And an important identity, which I will state now, and which may ring the bell for some of you. So we have again some relation satisfied by these new functions theta IKS, and now they are more interesting. They have the following form. If you take theta IK, 2 times theta IK, but with neighboring indices S and S plus 1, then what you get is theta IK plus 1, theta IK minus 1, S plus 1, plus a monomial in the theta gk, where j runs over the nodes which are neighbors to I in the Dynkin diagram. So in other words, the j for which the entry in the Cartan matrix is equal to -1. And so now maybe this reminds you about the mutation relations which we saw this morning in the framework of cluster algebra. This is no accident. This is going to be one of the exchange relations in the cluster algebra structure on this invariant subring. Okay, so now having prepared all these functions, I can state the main theorem of our first paper, that we have actually three cluster structure on these three rings. So the coordinate rings of GC bands, and then it's subalgebra of U invariant, and it's subalgebra of G invariant. So in the paper we give explicit description of initial seeds for this three cluster structure. Here I'm just giving a vague idea of how they are constructed, or what is more remarkable about these seeds. So the initial seeds consist only of some of these specific choices of coordinate functions like the one I have just introduced. So in particular for RGC, we get some initial seeds where all the initial variables are minus like this, with some appropriate choice of U and V and I. And in the case of the U invariant, what is remarkable is that we have a sort of canonical initial seed. Here we have many initial seeds of this form, but in this case we have a sort of unique initial seed with a very natural quiver, and this specific also choice of initial cluster variables. So here just take all the initial minus for all indices of the Dynkin diagram, and you vary with this S. And then there is a certain quiver with vertices labeled by exactly these functions, and you can find it in our paper. I will give you later the example of SL2, and this quiver will be, this will give you an initial seed for this cluster structure. And finally, for the G invariant, we also have an infinite rank cluster algebra structure, but now the initial seed consists of this function theta ik, which I just mentioned in the previous slide. Okay, so the main idea of the proof is to, well, we haven't said much yet about cluster algebra, but when you have a given ring and you want to prove that it is a cluster algebra, so the first thing is to kind of guess an initial seed. So I try to tell you that there is a sort of guess that you can make here, but then you still need to show that by mutating from this initial seed, you get exactly what you want. And so one difficult feature is that by construction, when you mutate a cluster variable, what you get is something which is a rational function in the other cluster variables. Well, this rational function happens to be a Laurent polynomial. This was stated by David this morning. But still, here we don't want, we want to stay inside our rings. So the coordinate ring RGC, you cannot, if you start inverting element, you may get out of the ring and go into its field of fraction. So you need something to ensure you that starting from this initial seed, if you mutate in any direction and you keep mutating, you will create things which are not outside the desired ring. You want to stay inside this ring. And this is, in principle, quite difficult because there could be infinitely many sequences of mutations to check. And so the so-called starfish lemma is a well-known lemma in cluster algebra theory, which tells you that under some favorable hypothesis, you can restrict all this infinite number of checks to a finite number of checks. So, and this, here we show that we are in a position to apply the starfish lemma. And then we have to use other things, but this is one of the main ingredients in the proof. Okay, so now I want to go to the relation with, these are the initial seeds. In the case of SL2, these are the initial seeds for this three cluster algebra structure. So in the case of SL2, we have 2 by 2 matrices. So the minus are delta 1, 1, delta 1, 2, delta 2, 1, delta 2, 2. And with the general notation, delta 1, 1 is delta pi pi, delta 1, 2 is pi c pi, and etc. Okay, and so here is the seed for the ring of bands. You see, it's like an infinite type A quiver, infinite in both directions. It's all the arrows are going up except one, which is going down. And this arrow connects this function delta pi pi to delta pi c pi. I mean, it's very nice combinatorics, but I don't have time to go too much into this. If we go to the U invariant, then we keep the same upper half, like this, but we continue it without this down arrow. It's like we forget about this and we continue regularly like this. So it just goes down, r minus 1, r minus 2, etc. And for the G invariant, now it's going to be a semi-infinite quiver. It's only infinite towards the down direction. And the elements, the initial cluster variables, are no longer delta functions, but some of these theta functions which I mentioned before. Okay, so now the relation with quantum affine algebras. So I said before that the motivation was to compare the cluster algebra that we had found in the category of representation, in a certain category of representation of shifted quantum affine algebra with some geometric model of it. So just by checking the initial seed, we can verify that the cluster algebra that we just described for BGC coincide with the cluster algebra that we used for describing this Grothendieck ring for the category O shift Z. So I hope that David will have time this week to tell us about this category O shift Z. But this was our main motivation. We knew what was the cluster algebra structure on this side, and then we found a geometric object with the same cluster algebra. And so this means that we have an initial seed which matches. So not only the quiver are the same, but we have a nice correspondence between the minus here, which label the initial variables, and here the element inside the Grothendieck ring, which are these Q variables. I told you that there are these QQ systems which are important in this thing. So the name QQ system comes from these Q variables. So I'm not going to give you the definition of this, but they will maybe come hopefully in the David's talk during the week. So we have this kind of correspondence. And similarly for the U invariant, so the U invariant corresponds to a subcategory inside here, namely the category of finite dimensional modules. So this category O, as the letter O may suggest, contains at the same time infinite dimensional and finite dimensional modules. But you can look at the subcategory containing only finite dimensional modules, but still shifted. And this one will have a Grothendieck ring, which will be isomorphic to this. So the U invariant corresponds to this, and here the correspondence is like that. So you can ignore this normalization factor. This is not very important. This is a particular case of Q function. These are called the positive prefundamental representations. Okay.
So and the category O is like the B module version?
Well, the category O was introduced by Drinfeld and by Jimbo and Hernandez.
Okay.
Yes, and so if you have, well, for this is one for shifted, so it's the same type of idea, but it's a different work. Okay, and finally, if we go to the G invariant, then we found a geometrical model for just the classical one. So these are the genuine finite dimensional representation of the quantum affine algebra of type ADE. And now the functions theta ik, which I mentioned before, correspond to the classes of some very familiar objects in this theory, which are called Kirillov-Reshetikhin modules, for those who know. And probably there will be some, they will be mentioned later in the week. So in particular, the function, the relation which I explained before about satisfied by this theta I, if you know Kirillov-Reshetikhin module, you know that they satisfy similar relations, which are called T systems. Okay, so now I have a quarter of an hour. It's a little short, but I will try to explain a little bit this Frenkel-Reshetikhin conjecture. So Frenkel and Reshetikhin in 1999 or 1998 define the Q character of a finite dimensional module over UQG hat. So this was briefly mentioned by David this morning. This is a notion of character that is appropriate for the finite dimensional representation of the quantum loop algebra. And the definition is similar. You take your finite dimensional module and then you decompose it with under the loop carton, right? And then you get something which are not eigenspace but generalized eigenspace, and then you just make some polynomials which count the dimension of the various generalized eigenspaces. And in this way you get an object which is very useful, which is called the Q character. Now, in the same paper, in the final section, Frenkel and Reshetikhin stated that for simply based G, there is an alternative method to find the Q characters of irreducible representation by using the Q-different Drinfeld-Sokolov reduction. And they quickly explained the case of type A, but obviously left it kind of open for the other cases. So, together with Luca, in our second paper, we were able to use the previous theorem about cluster structure to explain this conjecture. Okay, so I need to explain first the meaning of the conjecture. So this is why I prepared this Steinberg theorem before, because it's very similar to Steinberg theorem. That is a sort of loop version of Steinberg theorem. So remember that the coordinate ring of the cross-section of A is, can be identified in a specific way to the character ring of G. Now, when we try to calculate characters of G, what we like to do is to express them as sums of characters of the torus. So when you look at an element inside this polynomial ring, okay, you have a bunch of monomials in this chi1 and possibly some minus sign, but this doesn't tell you what is the dimension, for example, of, well, it's not so the usual way is you like to write a character as a sum of characters of the torus. And so here is a sort of strange way to obtain this decomposition, which we will then imitate in the loop case. So let me introduce this M. M is a double coset of the Coxeter element with respect to the unipotent subgroup. So by Steinberg, we know that this double coset is in fact included in the set of regular elements. All elements in this are regular. And then you can intersect it with the negative Borel. And you will get, it's easy to check, you will get some reduced double Breuer cell, for those who know what it is. But this particular one, in fact, as a geometric object, is just isomorphic to the torus. So let me show you the example of type A2, where everything is completely explicit. So in type A2, this M is just the subset of all matrices of this form, where you have one under the diagonal and anything above the diagonal, with the condition that it is in SL3. And then when you intersect this with B minus, which are the lower diagonal matrices, then you get some matrix like this with certain diagonal, and the diagonal is ones, and everything else is zero. So because these are ones, so you see immediately that this is, as an algebraic variety, this is isomorphic to the torus of diagonal matrices inside SLM. Right, so now what you can do using Steinberg's theorem is the following. Because this M, and in particular this LCE, is contained in the regular locus of G, it means that every element in here is conjugate to unique element in A. So you have a well-defined map psi from LCE to A, right? And now you can take the pullback of this map, and you will get a map from C of A, coordinate ring of A, to the coordinate ring of LCE, and LCE is the same as T, so you get a map from C of A to C of T. And C of A is just a character ring, so you can check that this is exactly one way of writing a given character, which is written as a polynomial in the fundamental characters, as a sum of characters of the torus. And now we're going to write a loop analog of this. So this is going to be called discrete Drinfeld Sokolov reduction.
So how the character of the module appears in C of A? I'm lost.
Let me go back.
So in C bracket A, so where do you find the initial character?
C bracket A, by definition, is identified with this polynomial ring in the fundamental characters. So if you have a character, you can write it as a polynomial in the fundamental character, and then, yes. Yes, so now we are going to replace G by infinitely many copies of G to the Z, and we are going to replace similarly U, M, LCE, A, the torus, everything. We are going to make it infinite like this. And yes, so the important feature of Steinberg's theorem was the conjugation action. Right? We said that every element in M, in G actually, in G reg, is conjugate to an element in A. Now we are going to change the conjugation, conjugating action on G. This will become the discrete gauge action on G to the Z. Namely, when we want to act with one element of GZ on 2H of S, we do some kind of conjugation, but here you have this S plus 1 instead of S. So you mix the S component with the S plus 1 component. So this is taken from the papers of Frenkel, Reshetikin, and Semenov-Tianshansky, which I mentioned in the beginning. This is a classical, apparently a classical feature, a classical object. So you look at this action, and then one thing that you can check is that if you restrict this action to the UZ, then so if you act not with G but only with U to the Z, then it will leave this M of Z stable. So you can look at the restricted action of U of Z to M of Z, and then you have another.
M again? M is.
So M is the double coset U C bar U. So what Frenkel, Reshetikin, and Semenov-Sebastianov stated and proved in a slightly different setting, instead of using, like I did, this I call discrete because we used G to the Z. But in their paper, they use instead the loop group of G. So our version is like a discrete version of the loop group somehow. But most of the things behave exactly in the same way. And for what we want to do, it's much better to have this discrete version than the loop group version. So the theorem is that this acts freely on that one, and A to the Z is a cross-section. So this is very similar to the Steinberg Steinberg cross-section theorem, and actually we found the reference to Steinberg in their paper, so they also knew, they were conscious of this, of course. So anyway, we have this theorem here, and this means that, like before, by by taking an element inside LCE to the z. So LCE to the z is contained inside M to the z. So M to the z is conjugate by under U to unique element in A to the z. So we get a map like this. And this map they call the discrete Murat transformation for good reasons, which I'm not going to explain. And now you can, like before, pull it back and you get a map from the coordinate ring of A to the z to this coordinate ring of infinitely many copy of LCE, which is another version of this. Okay, so now we are ready to, almost ready to state the Frenkel-Reshetikhin conjecture. We have to do some identifications. So, first of all, the coordinate ring of A, I said, this is isomorphic to the character ring of G. But the G is simply connected, so the character ring of G is the same as the character ring of its Lie algebra. And we know also that if Q is not a root of unity, as a based ring, this is isomorphic to the character ring, to the Grothendieck group of the finite dimensional module over QG. Right? So now the good way to think of C of A now is as a complexified Grothendieck ring for the finite quantum group. And now, if we replace A by A of Z, so in fact we are going to have the same, but where we replace the finite dimensional representation of UQG by the finite dimensional representation of the loop, of the quantum loop algebra. And the correspondence is that you should send the variable which I denote by theta I1 before, so the polynomial generators of this ring, they should be sent to the classes of the fundamental modules in this category. So now this is one isomorphism, and then if we go back to the torus, so I said before that this is isomorphic to the coordinate ring of the torus, and the coordinate ring of the torus is a Laurent polynomial in some variables yi. So small yi means the formal exponential of the fundamental weight pi I. Right? So you can express classical characters as Laurent polynomial in these variables yi. And then the Q character is built in such a way that you can do the same for the quantum affine algebra, but now instead of small i's, y, you have capital Y's, which depend also on some spectral parameter here. So this is a classical notation which goes back to Frenkel and Reshetikhin. So we get again a polynomial, a Laurent polynomial ring in infinite, but now in infinitely many variables. And now the theorem is the following. If we do the corresponding identification, so if we identify C A to the Z to the complexified Grothendieck ring, and also this one to the Laurent polynomial ring in which the Q characters live, then by construction from Frenkel and Reshetikhin, we have a Q character which is a morphism from this to this. So it means that it takes a class of a finite dimensional representation and expresses it as a Laurent polynomial ring in the Y's, where you can, from this Laurent polynomial ring, you can read the dimensions of all the generalized eigenspaces for the action of the loop Cartan. And now what is the conjecture is saying that this ring, modulo this identification, is identified with the pullback of the discrete transformation, Murat transformation. So I think my time is over. I don't have really time to explain the proof, but let me just say that it relies heavily on the cluster structure, which I explained in the first, it uses several ingredients, but maybe the main ones are the existence of the cluster structure for this algebra, and also, strangely, for the U invariants. You remember the U invariants which correspond to the finite dimensional representation of O shift. And the second important ingredient are the so-called extended Baxter relations of David and Edward Frenkel, which allows to express the Q character of the finite dimensional representation. I mean, it's a way of starting from the Q character of the finite dimensional representation to obtain a certain relation in the Grothendieck ring of this category of finite dimensional shifted. So you replace every y by a ratio of two classes of prefundamental representations. So I think I have to stop. Thank you.
Any questions?
Yes.
So the QQ system, the extended one with the W's, these relations between Q of W, omega is a hard conjecture of David and Frenkel, right? So
Say it again, which conjecture?
the QQ system, so the relations between the Q, W, omega and so on.
Yeah.
Does your approach prove it, or does your approach translate it into something geometric?
No, well, first of all, when I said before, yes, so when I stated here that our geometric model correspond to these Q variables, I didn't say that these Q variables are classes of simple objects.
Okay.
This I don't know. These are just some expressions which are conjectured to be classes of simple objects.
Ones which David and
Yes.
introduced.
And so that would be, of course, very interesting, but we don't yet know. We know in some cases, of course, but
Because I know in their paper one of them is a straight Q and the other one is curly Q, so maybe I should have paid more
well,
attention to
we
the
have
one.
underline Q, which means slight renormalization also. So, but yes, this is indeed.
Have you tried to put G hat C bands? Does this make sense?
G hat?
Yeah, a loop group of some kind. Does this break down?
What do you want to put G hat?
Well, I guess I wanted to see different cluster algebras appearing, which, I mean, adding some other level of affinization somehow. You're seeing shifted affine. Like, could you see shifted toroidal? Introducing some.
Okay. Yes, toroidal. We didn't think about it. Actually, I don't know, but it's a good. It seems that yes, what we see in this week, there are various things which extend to toroidal. So maybe also this would be something to try. But no, I don't have anything to report on this.
Is the choice of the Coxter element somehow important here, or is just some arbitrary?
No, and actually this is one thing which I like, that in our approach we work uniformly with any Coxeter element. And for example, in our proof of this theorem here, yes, this theorem here, so I put their names and I put our names. In fact, in their case, the proof is a little bit terse. It's just a one-page proof, and for some reason, I mean, from what we understand, it seems that they use a specific choice of Coxeter element for each type, and then also, for even more mysterious reason, they seem to avoid the type E6. Is it E6 or E7? E6, I think. So E6 is not contained in their proof. Whilst for us, we do everything uniformly without.
Other questions?
At which step is it necessary to assume that we are in a simplest case?
Yes.
At which step is it required?
Very good point. So, for example, here we don't need it. This is true also for non-simply laced case. So the place where we need the simply laced case for the moment is, for example, here. Yes. In this paper which we wrote with David and Christophe, we only treated the case ADE. So we are now working for a long time on a generalization to non-simply laced case, but still things are going to be more complicated if we want to relate this geometry. And so, in fact, here you can, of course, define this BGC for G non-simply laced, for example, type B or type C. There is no problem of like this, and what we think we have not written it down properly, but we believe that we would get again a cluster algebra structure, which would generalize not the cluster algebra, which would continue to generalize the cluster algebra on the coordinate ring of G. Right? In this case here, what we do is some kind of affine analog of the coordinate ring of G. So this would continue to be the same if G is non-simply laced. But then if G is non-simply laced, what you get is the cluster structure is not skew-symmetric anymore. It is only skew-symmetrizable. This is well known from the early papers of Fomin and Zelevinsky. And on the other hand, in the paper which we are preparing with David and Christoph Geis, for G non-simply laced, in this category here, we find skew-symmetric again. And for example, here it's already known that we find also some skew-symmetric cluster algebras. So these two cannot match. So we cannot really just keep the same definition if we want to match with the quantum affine algebra side. But perhaps there is a way to twist the definition of BGC and to get something that matches, but for the moment it's not known.
But the Frenkel-Reshetikhin conjecture can be stated uniformly for...
The Frenkel-Reshetikhin conjecture is only for type ADE.
It is?
Yes. So as I wrote here, yes, this is because of this. So how do they obtain this conjecture? This is using the W-deformed algebras, right? So the point is that you start from this WQT, right? And then you can specialize either Q to 1 or T to 1. And so one of the conjecture is, so let me see if I say it correctly. If you specialize T to 1, then you get WQ1, and this is always isomorphic to the Grothendieck ring, right? Yeah. But on the other hand, if you specialize Q to 1 and keep T, they conjectured, and I think it is still not proved, that what you get is could be obtained by Drinfeld-Sokolov reduction starting from G. Okay? And now, in order to relate, so apparently it's a different direction. It doesn't go in the direction of skew characters. But if we are in type ADE, then the parameters Q and T may be easily reversed. And in this way, you can connect the two features. But if it is not simply laced, they don't...
There isn't like a Langlands duality?
Yes.
D1.
Sorry?
Oh, there isn't like a Langlands duality where you degenerate one way?
Maybe. I don't know, but they don't mention it.
The Steinberg theorem?
Sorry?
The original Steinberg theorem is for all...
The original Steinberg theorem is for all types, yes. Yes. So this is similar to what I said about the new... this version here is also for all types.
Well, let's save questions for later and let's thank Bernard again.